In regular X-ray imaging, we just see through an object, like this alarm clock here. But in tomography, we solve an inverse problem to get a slice image. And we can do that for a live human person. That's called science, folks. In this video series, I reveal the mathematical secrets behind tomography. Imagine putting something in front of an X-ray source. For example, a yellow rose. Then switch the source on. Actually, X-rays are invisible to the eye, but I added the purple cone for clarity. Place an X-ray camera on the opposite side and you get an X-ray image. In the dark areas of the picture, there was nothing in the way of the X-ray. Lighter colors mean that the X-ray was weakened by traveling through material. The more stuff the X-ray passed, the lighter the pixel in the image. The most classical application of X-ray imaging in medicine works by putting not a flower but a patient between the source and the camera. Then the doctor can see, for example, broken bones. X-ray imaging is also useful for non-destructive material testing. This particular test, though, is a slight bit destructive. Let's get to the main topic, X-ray tomography or slice imaging. Namely, you cannot take a picture like this by just putting the patient between the source and the camera. Tomography needs several measurements and some cool mathematics. A modern CT scanner looks like this. CT stands for computerized tomography. If we open the lid, we see this half-a-ton donut-shaped instrument rotating and measuring X-ray data from all around the patient. I'm glad that they usually keep the lid closed. Let's see how the very first CT machines worked, because it's easier to explain their parallel beam geometry as opposed to the modern machine's spiral geometry. Meet the original EMI brain scanner from the 1970s, invented by the Nobel-winning scientist Godfrey Hounsfield. While the source moves, we measure the amount of stuff in the way of the X-ray. The result is recorded as the yellow profile function. Zero value in the function means there was nothing in the path of the X-ray. A high value means that there was a lot of attenuating tissue, such as bone. The source moves linearly along this side, but the machine also rotates. It's essential for tomography to collect the yellow profiles along many directions. Here I'm showing the measurement process really fast, not stopping the rotation for the linear movement of the source. Now we arrive at the inverse problem of tomography. The scanner gives us the yellow profiles, and the question is, what is the object that has exactly those profiles? We need a mathematical method for reconstructing the slice image from the tomographic data recorded by the scanner. The most classical tomographic inversion algorithm is filtered back projection. I will explain it in detail in the later lectures. Let's close the video by looking at an important medical application. In ischemic stroke, a blood vessel inside the brain is clogged by a blood clot. A part of the brain is then not getting oxygen. If this goes on for several hours, that part of the brain is lost forever. However, if blood thinning medication is started quickly, a full recovery is often possible. Another type of stroke is caused by hemorrhage or bleeding in the brain. Here the white patch is blood where it's not supposed to be. The trouble with stroke is that the symptoms of both kinds are exactly the same, but the treatments are very different. Blood thinning medication is good for ischemic stroke, but outright dangerous for the hemorrhagic stroke victim. It's very important for the doctor to know which kind of stroke it is, but the symptoms won't tell that. Well, tomographic slices show the difference very clearly. Ischemic is dark and hemorrhagic is bright. Thanks for watching and look out for the next videos in the tomography series. Now it's a good time to subscribe to my channel and turn on notifications. See you next time.